plus infinity in the reciprocal space. And if I consider this is, let's say, case 1 in which a is very small, and let me discuss case 2. And case 2 is such that if a is very large, so what will happen? If a is very large, means a is very greater, then what will happen? That this value, when it is sharply peaked at 1 over 2a, when 1 over 2, when a is very greater, then this is in the reciprocal dimension, so this sharp peak will come like this. And let me plot this one as well, that this is our axis, this is our x, and here I am having psi of x0. When a is very large, then 1 over 2a will be very small, and this will behave like this, that this will be 1 over 2a. It will be just like the momentum, that this value becomes small, means it was first restricted, now it is enlarged. And for phi of k, if I plot phi of k here, means k on this and phi of k here, then I know that phi of k is equal to 1 over pi a sine ka over k. Now the value will be, is this one will now, this one has gone, means now the space is not restricted, so the momentum will get restricted into, means the wave function will get restricted in the small space of in a small k space, so it will be now shortened. So let's see that what will happen. Now we cannot apply limits here, but we can see from here that it will be in the momentum space well defined. And if I look at ka sine ka, then this is equal to sine, and is k will get different values like this. So what I will see here, like this is one value, another and another, and so on. Let's say I give different values to k, but I know that for a value when k is equal to pi over a and I apply a, then sine phi is equal to 0. So if this value is pi over a and this value is the same as minus pi over a, then I know that the wave function r phi of k will have 0 value. So it will touch here, but in the range which is beyond this one will be again equal to some value, but not with that amplitude, not with a over pi amplitude, but with a small amplitude, and again it will touch 0 here as well as here. So I can write that if this value is pi over a, if this a over pi, if this value is a over pi, then this will, as it's a sine function, so sine function, the wave-like form, it will go like this, and similarly it will go like this. So this maximum value is a over pi square root, while it will become 0, and again it will rise and become 0 here for minus 2 pi by a, and similarly here for minus 2 pi over a, and so on. The amplitude will be reducing as we will pass on is we will pass on, the amplitude will reduce. So when x is sharp, then p here are p is equal to h bar k, so k is broad. And when x is broad, then k is sharp, which is according to the Heisenberg uncertainty principle, which we will discuss after some time. So psi x0 here, it has become broad because A is very, very large, and this one became sharp as a result, and it is passing through some 0 points because it's a periodic function, and as it goes on, the value will be decreasing and so on. Now we are in a position to discuss that what is the phase velocity and what is the group velocity, or we can understand the difference between the two, as our wave function was psi of xt was approximately, means I will write only the exponential portion, ei k x minus h bar k over 2m t. So here, if I look at this portion, then this portion is actually v, and I can write that v, which is our quantum mechanical speed, so I'm writing quantum, and this is equal to h bar k over 2m. Now I can write this in terms of energy, and as I know that E is equal to p square over 2m, and p is h bar k, so it is h bar k square over 2m. So I can write this thing is, if I divide this one by 2m and I take square root, then I will have to divide this one by 2m and I will take the square root, so this will become 4m square and square root. So this will be equal to h bar k over 2m. So it means that h bar k over 2m is actually equal to E over 2m. Now, if I want to derive the classical velocity, or the velocity for a classical particle, then I know that E is kinetic energy, which is equal to half mv square. Now this v is actually classical, and from here I can write that v classical will be equal to E over m, 2E over m and square root. So this is quite strange that our classical velocity, that our v classical came out to be equal to 2 times the quantum mechanical velocity. So v classical, because here it is E by 2m, if I multiply this with 2 here, if I want to make this 2 here, and it is divided by 2 here, so it will come 4 times. If I multiply 4 with this, then it will become 2e over m, and 4 when come out, then it will become 2 and e over 2m. So we got that the classical velocity came out to be 2 times quantum mechanical, and this is really very surprising. But in fact, we are not differentiating between the two things. Let me explain this thing, that here this will be that why this dilemma is arising. This discrepancy arising due to some miscalculation here, and we will now find out that what is the problem. I can rewrite my expression, and this expression is that I can write this, if I multiply kx, then h bar k 2mth will become k square, and this will come out to be omega kx minus omega t. So if I want to convert this into omega, then I will do multiply this k inside, and from here I will get that omega is equal to h bar k square over 2m. So it will come out to be omega. Now if I write that omega over k from here, if I write omega over k, then it will be equal to h bar k over 2m. And this omega over k I define is phase velocity. So the h bar k over m, which I was calling the quantum velocity, is actually the phase velocity, and the group velocity g is d omega over dk, and d omega over dk 2 and h bar k and 2 will cancel, so we will get h bar k over m, and h bar k over m is actually equal to from this expression h bar k over 2m. Now this was earlier e over 2m. Now here we don't have any 2 here, so it will give us that the classical velocity is actually equal to h bar k over m, and if I compare it with this one, then it comes out to be 2 times v h bar k over 2m, so it comes out to be 2 times the phase velocity and equal to v classical as well. So the phase velocity and the group velocity are actually the difference between them is the reason that we were having this discrepancy. Now in order to understand the difference between phase and group velocities, let's say we are having different waves and they are having different speeds over here, and when they combine with each other, means when they do interfere, we are having this form of the wave. So after the interference, we are having a wave which is having a definite speed, and it is like this, that inside this envelope we are having many individual velocities, but the envelope as a whole is traveling with a group velocity, while inside we are having phase velocities. So phase means different waves inside this envelope will travel at different speed, while the envelope will travel at a different speed which we will call is a group speed, and this will be the classical speed which we call the group velocity. Now to understand this thing more here, the phase and the group velocities, we will have to put two things to us, that when waves are traveling with phase velocity, so v phase, it may be equal or greater than the speed of light, and we call them the phase of the wave fronts. The wave fronts are those which are called the phase of a wave. The wave fronts don't carry energy. The wave fronts don't carry any energy, while the group waves carry energy. So how this can be greater than the speed of light? Because we talk the energy, we call it information. So different waves, or the waves that are traveling with a phase velocity, are not carrying any information, but only the envelope or the group of waves carry information. Let me explain this thing in a different way. Let's say I am having a group of 6 students, and this group of 6 students, to each of the student I have given a single alphabet or single letter, and let's say that letter is silent. So now I want to convey this code word which is silent. Now this is, each of the student is having one word with them, and they are going to carry this information somewhere. Now if, for example, each of this letter or each of these students is actually phase, or this L goes earlier and all this. Now the information that is going early means, let's say we say it moves beyond the speed of light, then individual letters will have no information in them. They will not be able to deliver my code word, and the code word will only be understood when all of the students gather there and display their each letter, and the word will come out to be silent. So this whole word will actually travel with the speed of light, while individual word may go beyond the speed of light, but it will have no information, it will have no energy with them. Now the same word means the same letter can give this word as well. Lesson. So silent, the same number of words means the same words will utilize, then the word will come out to be lesson. So then how one will understand whether the code word is silent or whether the code word is lesson? So to realize this thing, the student should stay in proper order. Like for example, they were being given information that what your order will be, and that order will actually call, in the terminologies we call it modulation. So they will be properly modulated. You know that we say that this is in the radio channel we say that this is AM. So the modulation is done with the help of amplitude. So we say this is amplitude modulated. Or we say that we are hearing to the FM, and FM is the modulation which is done with respect to the frequency. So it is frequency modulation. So modulation is also important, and this modulation is actually the one which is putting energy or information into a given word. So phase can be equal or greater than the speed of light, but the group velocity, the Vg, will always be equal to the speed of light and cannot be more than this one. So this way we understand the phase and the group velocities.